thank you very much for setting this up. It's really a wonderful opportunity for me to share work that is really a group effort, an outsourcing training of sensitive medical secure multi-party collaboration. And when I say it's a group effort, it really is. Here's a wonderful team that's working on this. And I want to particularly call out to Regina, who I know is in the audience. She's really the reason I became involved in this project. We were discussing things while our boys were doing something else. And we ended up finding so many common areas of interest, in particular, sort of a bit more of an information theoretic view of what it means to be private. And you know, one thing led to another, and here we are, you know, basically just less than 2 years later, really looking at a very fertile set of problems and new methods. So here are the collaborators. I know that apart from Regina, I can't see the audience, but I know Adam is there, so is Homa, and I also want to call out our collaborators.
Victor is there.
Pardon?
Victor is there.
Victor's there. Okay, Victor, again, I can't see anybody, but also my other colleagues at MIT, Manya, Tommy, Vinod, and also Ken Duffy from Maynooth University, who heads the Hamilton Institute there. All right, so what are we looking at here? Why do we care? You know, that we should always start a talk with, you know, what and why. And I think this notion of having you know, different forms of federated learning is really something that has gained a huge amount of traction, as many of you know. Some of you may have heard of all the issues around FLoC, the federated learning systems that were declared to be non-GDPR compliant, particularly the Google version was declared to be non-GDPR compliant in Europe. You know, this is a hot area, but it's also an area that is that in a way is truly necessary if we want to make use of the richness of data that's available over a wide variety, highly heterogeneous and diverse set of owners. Okay, and the idea here is that, say, you have a center which is trying to make use of the data which is available across different owners and possibly different stakeholders. And you want to be able to learn in a way which preserves privacy. So, you know, and you see here, for instance, in a hospital, you'd like to be able to use the data for training a model which involves the benefit of data from multiple stakeholders, multiple hospitals. But of course, those hospitals need to be very careful with the privacy of their users, of their patients. Okay, so we can't just take all the data and, you know, send it to one centralized location, not only because that would be just a staggering amount of data, but because it would be highly insecure and possibly a breach of all kinds of privacy regulations. So how do people deal with this? So sort of the more heavy duty approach to this is homomorphic encryption. It's basically encryption which you can operate on, right? Hence the homomorphic part of the name. There are methods for doing that. Vinod, one of our collaborators, is actually specialist in this area. Many of you who may be following the domain may have heard of the recent announcements from IBM for their homomorphic encryption products. The problem is that they're very, very onerous from the point of view of computation. You know, IBM is telling you that you should expect basically about 100-fold increase in the cost of your training or more. So 100-fold is about a lower bound. It also often requires you to modify the machine learning algorithms because this homomorphism is dependent on the particular models of the machine learning. And they do entail a loss of accuracy, which of course is a very subtle dance between the kind of encryption that you're doing and the types of ML algorithms that you're using, the computation. So it's a highly sophisticated, but also I would say highly onerous and somewhat fragile approach. But fantastic from the point of view of security. The other types of methods are standard differential privacy methods. There are plethora. There's, of course, a large literature devoted to that. And probably while I have been speaking, 2 or 3 other papers have appeared in the domain. The main idea here is to distort in some way the data, adding some noise to it, so as to obscure maybe private information or sensitive information, but that addition of noise comes at the cost again of accuracy. And so it's again a subtle trade-off between adding noise which distorts the data in a way which makes it less recognizable but also less useful. Okay, distortion methods are again somewhat similar to number 2. I would say that a lot of the differential privacy methods are a little bit related to number 2. And many of these distortion methods were originally designed more for issues of privacy when the concern was around, let's say, people looking at something and recognizing it. But many of these have been shown to be actually quite fragile on attacks which are more done by AI and machine learning approaches. Maybe more closely related in philosophy to what we've been doing in this project are 2 different approaches which rely in effect on doing coding. Coding is a processing, generally an algebraic processing of the data, linear or nonlinear. And it's a sort of thing that is generally done, for instance, for compression of the data, for getting a more efficient representation of the data in storage. It's also done for making the data more reliable by adding redundancy, for instance, in communication channels or also in storage to protect against bit rot. And there has been a lot of interest lately. Here are a couple of methods with I'll give you the references at the end, which look at basically using coding type approaches to pre-process data and see whether those approaches provide some level of privacy, while at the same time maintaining the learnability quality of the data. Okay, and in particular, there's 2 of them that we're going to use as comparators in this talk. One of them is InstaHide and related mix-up techniques. InstaHide does a linear mixing of samples from images ahead of doing the learning on them. And Dauntless, which is encoding images using a neural network, and then considers security with respect to a plain text attack. Okay, I just want to take a little bit of time, just a couple of slides, and with all appropriate apologies to the people who are security experts. This is really just so that we all think of the models in a sort of consistent, common framework. What is perfect security? Going back to Shannon, right after World War II, he had, of course, been working on the same project as Turing. He had been working on on cracking the Enigma machine. And so, that there had been a lot of thinking collectively about what it meant to have perfect security. And perfect security is the one-time pad, which is that if I look here on the left at the plain text, so the data say that I'm trying to preserve, and I look on the other side here at the ciphertext, it would mean that for any ciphertext, for any encoded message, all possible pre-images would be allowable. That's to say that looking at the ciphertext did not in any way limit the set of pre-images. Okay, and that's in effect what the one-time pad, what perfect secrecy would be. Now, that's not what we do. We use different kinds of encryption or hiding. And the idea behind a key, an encryption key, so whatever the key size is that the pre-image of the ciphertext is mapped back not to all possibilities, but to a set of possibilities, which is of a cardinality that is exponential in the size of the key. That is to say, if you have a key of, say, 10 bits, then your pre-image is 2 to the 10 possibilities. And good cryptographic systems make it so that within that pre-image, there's no particular similarity. Okay, so yes, it's not the set of all possible messages. However, those messages appear as close as possible to. Sorry, there's somebody right against the. Oh, sorry. Thank you. That pre-image appears as being as close as possible to randomly picked from all the possible messages, so that there's no particular pattern in the pre-image of a ciphertext. Okay, so that's really what a key size is. It's the size of this pre-image. Okay. So what does that mean for us? Well, what that means for us is that if we're going to be doing some sort of coding technique where, this is the coding that we're doing, this is the mapping that we're doing, this is the ciphertext, in fact, even though it may not be encrypted in a traditional way, what we're going to be looking always is at some notion of the properties of the pre-image, that's to say those original images. So these would be, for instance, test X-rays that would be found in this pre-image, in this original possible set. Okay. And in particular, one of the things that we can consider in healthcare and in our applications is that, unlike, for instance, what people are trying to do in homomorphic encryption, which is, as I said, a very heavy-duty technique, we're not, for instance, trying to hide the fact that we have, say, X-rays. If you have a system which is gathering information from different hospitals in order to train on X-rays, you don't need to hide the fact that the image looks roughly like this. Again, homomorphic encryption is a far more stringent set of requirements, has a far more stringent set of requirements. So they would like to hide just about everything about the image. Here, that's not the case. We know that if it's an X-ray, it's going to look roughly like this. What we don't want an attacker to know is, if an X-ray is transmitted, whose X-ray is it? And can we decouple, in effect, the connection between the X-ray and the original image, which might lead to identification of whose image it was. So in effect, what we want to do is we want to have a system which is going to transmit this coded data. And even though an attacker is going to look at the encoded data and say, oh, well, I wonder what it is, they're not going to wonder, is it an X-ray? Well, with good chances it is an X-ray. And if it is an X-ray, with good chances it looks something roughly like this. What we're really trying to avoid is the identification of the specific X-ray, of whose X-ray it is. And that way we're trying to keep the privacy. So this pre-image here is already an image, not in unbounded set of possible images. And by the way, this will be important later for some of the attacks that we look at. So that's why I want to bring this up early, because when we look at some of the later attacks, I'm going to revisit this issue of the images. We know that there are images in there. Everybody knows that there are images that are roughly looking like this. Okay. So when I'm talking about this pre-image set, it's already a pre-image of, you know, X-rays, chest X-rays even. Okay. Okay. So what we'd want to do is we would like to encode on the raw data with very lightweight functions. And then we'd like to publish the encoded data and the associated labels publicly. Okay, so remember when we had this multitude of stakeholders, this multitude of different sources of data, what they're going to do is they're going to provide an encoded version of the data, and it is on that encoded version of the data that the training is going to happen. All right. So how do we do that? We're going to take the usual the usual terminology from cryptography. Alice is trying to transmit to Bob, and Eve, the adversary, the eavesdropper, is trying to butt in and figure out what Alice is telling Bob. Okay. So Alice, in our case, is the legitimate owner of the data. It's the owner of the sensitive medical data. Bob is the machine learning specialist who's trying to train, say, a classifier for the examples that we're going to look at in using the label encoded data that Alice is providing. And Eve is going to be looking at the encoded data and is going to try to retrieve sensitive information about the data that Alice is sharing with Bob. Okay. So just a little bit of notation, If I look at the set of the encoded samples, which is the original data, let's call it X, Z is the encoded samples. A mapping from X to Z, which is bijective, is what we're going to be calling an encoders. And we're going to have a family of encoders from which Alice is able to select the encoder that she's going to use to provide the data to Bob. Okay, and basically what is Eve at the first step interested in doing? It would be to figure out how is Alice encoding the data. If Eve is able to figure out how Alice is encoding the data, then Eve might be able to then look at data later that is available that's made available to Bob and try to undo the encoding, sort of reverse the encoding process. So figure out that pre-image of the data in the terminology that we've used before, and therefore be able to figure out the sensitive data. Okay. So Alice is going to have her private samples, and she's going to select a means of doing the encoding. So going back to the terminology we used before, you know, imagine in a cryptographic system, Alice is going to select a key. Okay, she's going to select a key in order to be able to parameterize which scheme she's using. Okay, so think of this selection as being a key, and she's going to encode her data according to this selection of the encoding function, which is, you know, the secret. Now, Bob is going to receive the label encoded data, is going to train it, and is going to use it for training a classifier. So again, what is Eve going to see? Eve is going to try to find out what this TA is. What was it that Alice chose to encode her data? Now, like in all of these systems, as I mentioned before, there's a tension, there's a trade-off, there's a tension between privacy and learnability. Of course, you know, if you just sent the data unencoded, if you just sent the plain text, that would actually be your perfect learnability. That's the best that you can do from a learnability perspective. The perfect privacy would be to send absolutely nothing at all. But of course, that would be zero learnability. So what we're always trying to manage is this tension. I mentioned before, some other schemes try to do it by adding noise or doing some sort of distortion on the data. We're going to be taking a somewhat different approach. All right. So how are we doing this? Let's look at the samples with particular labels. Okay, let's think back at this idea of the pre-image. If my system is such that the encoding allows the learnability of the labels, and posterior to that, if providing an encoded image allows appropriate labeling of it, it has to be that the label itself is not going to be a private element, right? Because otherwise, sort of, it's almost a tautology. If it is that the label can be learned, then it cannot be that the label is private, because it can be learned. It can be deduced from the encoded data. So the best that we can do is to have that pre-image be within a label. Okay, so basically we can only have intra-label privacy. Otherwise, we are not going to have the learnability. So this is, if you will, ab initio, the first step in a limit of what it is that we can keep secret. We cannot keep the label private. Okay. So within the universe of all samples, the largest size of the pre-image that we can ever hope for is the entire set of images that have a particular label. Okay, that would be the ideal for our notion. So we have developed a system here, and particular shout out to Adam and Homa and Rafael de Oliveira, whom I didn't mention, one of my postdocs. Homa is also a postdoc in my lab, and of course, Adam and Victor are our students in Regina's lab. Our method is based on passing training samples through a random deep neural network, and then publishing the label encoded samples for the ML developer, for Bob, to use. Okay, so Alice is choosing randomly an encoder from a family of encoders. Remember that family F of encoders. Basically, that key that is chosen is the key is the selection of which of those encoders she is selecting in order to do her encoding. And the question is, how do we construct a good family of encoders? Well, there's an interesting theory here, which is that composing families of encoders can only preserve or increase the privacy of the scheme. Okay, so this is an informal statement of a theorem, but the theorem is actually formally proven. Okay, so in a way, it's intuitive, but it does require careful proof, and indeed that is what we have been able to do in our work. Okay, so that was just for having Alice, Bob, and Eve. But now think that I have multiple Alices, because remember, our goal has been all along to facilitate a secure multi-party system, a federated learning system. Okay, so Alice is not just one hospital now. We have multiple Alices with multiple data sets, and each one of these Alices is going to create their own mapping. Okay, so each of these Alices is individually, separately, independently picking a mapping of their data onto a coded version of their data. Okay. So let's look here at what it means in practice. So we have medical diagnosis. There's 5 of them. So these are going to be our labels. Remember that the best that we can ever hope for is for intra-label privacy if we're going to remain learnable. And in this case, we have 2 hospitals. So basically, we have 2 Alices. Okay. And these are the 2 data sets, available. So hospital 1 and hospital 2 are being represented by 2 publicly available data sets of chest x-rays. All right. So remember the different types of diagnoses. So those 5 diagnoses are shown up here. Okay. And the first thing to notice is that the combined data, if you look at originalized without the encoding, the combined data is giving you overall a benefit. Okay, so in some cases, the benefit might be slight. In other cases, the benefit is actually quite marked. You can see here, for instance, for the second diagnosis, you see a very marked benefit. In other cases, there isn't that much. But on average, you definitely do see it. So let's see what happens with the encoding. Remember, the best that we could hope would be that we don't lose any of the learnability by doing the encoding. And indeed, we don't see a loss of learnability from the encoding. Surprisingly, in some cases, you see a gain. I mean, obviously, sometimes you see a loss and sometimes you see a gain, but overall, you're really not seeing a loss of learnability from having the encoding. So this is basically about as well as we were hoping for, which is not to have a loss of learnability from the encoding. Now, how secure is it? Well, let's look at a couple of attacks, okay? And the reason for looking at these attacks is because recall at the very beginning of the talk, I mentioned a couple of other approaches. I mentioned the particularly the sort of the mix-up style approaches. Yes.
Are we supposed to understand how the mechanism works yet, or are you going to tell us that later?
The mechanism, yes. So the mechanism, I actually haven't talked much about the mechanism. That's a good question. I don't know who asked the question. Sorry, who was it?
This is David Sontag.
Okay, great. Hi, David. The mechanism is the following. We have a random deep neural network, okay? In this particular case, we used ReLU functions, okay? And then we published the label encoded samples. But we haven't told anybody which of these we picked. Does that make sense?
I understand the encoding. I don't yet have intuition on what you do with the encoded samples for machine learning.
I see. So what we do with encoding samples, thank you, that's a good point. So what we're doing with the encoded samples is we are publishing. So each of the Alices is publishing those encoded samples. And then those are being published and they're being used for training. Remember, the labels are provided. Okay, so basically I have the encoded samples with the label associated, and those encoded samples are being used to train models in order to be able to do the labeling later. Does that make sense, David?
Not yet.
Okay.
In a sense that, right, suppose that this transformation was a random permutation of all the pixels.
Mm-hmm.
Then it would seem to mess up, for example, use of convolution in a later machine learning step. So there's something I feel there's a piece I'm not yet understanding. Perhaps it has to do with the particular architecture you're using here.
I think that the point that you're making, which is, let me try to rephrase. The point that you're making is that if one does these sorts of transformations, one may then be restricting what kinds of algorithms Bob may deploy in order to learn on the data. Is that the point that you're making?
Yes, and I also just don't. So Bob doesn't know which institution it came from, right? And so does that mean the capacity of the downstream learning model has to be higher than it would otherwise be because it has to somehow learn a different function? I'm missing part of the story.
Maybe Adam can elaborate.
Yeah, so the utility number that you see, so is based on the particular design of the encoding scheme. So the Bob knows the encoding scheme. This is a specially designed node that's pixel shuffling at the end. It looks like the encoder of the vision transformer.
So Bob knows the encoding scheme, but not the parameters.
Not the parameters of the encoding scheme.
So how does
That's
Bob,
right.
How does Bob use that
You
knowledge?
train on the random features, and you know the inductive bias of the feature generated. You don't know the weights.
Ah.
Full parameterized, so there's no compression involved. So Bob can then model that signal and develop models. So the numbers that you saw there are Bob. He doesn't know what the transformation was.
But he can simulate it in some sense.
Yeah, but he doesn't even need to, because you have basically the inputs which you have to vision transformer. So the numbers that you saw there, the vision transformer is trained on the random feature encoding versus end-to-end architecture.
Yes.
When you train everything, it's like
I think I understand it a little bit better now, but maybe if other people ask questions, it would help. I would be surprised if everyone understands it at this stage.
Okay, so Adam obviously, as always, addressed it beautifully, but I just wanted to go back to this side. Maybe I hurried a little bit through it, and I think this is the crux of your question, David. Here, you see this encoding, the parameters, as what I was calling, in effect, the equivalent of a key in crypto. That's what Alice has picked, okay? And Bob does not know it, neither of course does Eve.
That's clear.
Okay.
Additional detail that all of the public data is the same private key. It's not like you're doing an independent transformation.
Per hospital. Yes, that's clear. So.
Per hospital, yeah. So as I mentioned, and I should have, each hospital has their own mapping, their own transformation.
There's still a piece of the story that is not clear to me.
Can I add something?
Yeah, please.
Only the hospitals that contribute data can use the train model. So that train data can only be used on trained sample. Although Bob doesn't know the encoder, but for using that encoder, that sample encoder is needed.
Yes.
It is like transferring the information to a new representation that hides some information for privacy, but because it is labeled, it can be trained. But for using this, we should transfer that representation. Yeah.
So that is also clear to me. But so first question is, what is your architecture of your downstream model? So what is Bob's architecture?
In this case, it's all vision transformer.
All the way.
Vision transformer.
What is that?
Transformers, meaning with the NLP model.
Yeah.
But the vision variant, which then looks at secret pixels.
Yeah.
And then uses the location to remember the architecture. So given the inductive bias of the encoding family, which everyone knows on the weight, that is architecture you want to use. And we can
Is there a way of mapping from the encoding architecture to what the architecture is that you should use?
So I think
there's another comment related, but I don't know if
other people can ask questions to be clear to me. I suspect we don't get it yet.
Just to check. Does Bob know which hospital each image is coming from? So can you condition on the parameters, but can you condition on which set of parameters?
In general, we did not, in the numbers that you'll see, we did not do that conditioning, but no one in hospital did that. And for example, they only use the architecture.
Yeah, it's pretty easy for that.
And from the notion of which architecture it is, the inductive bias obviously guides the model, right? So if there was no shuffling, you might want to use CNN. If there's pixel shuffling, the vision transformers give you the right kind of inductive bias. And so there's a kind of joint design problem on the side. But what it shows is that you don't lose, because the information is still preserved, you don't lose that much signal relative to these things. But I'm happy to also go much more depth offline.
Others don't have questions, and you should move on by all means. Thank you.
yeah, let's
great. Fantastic. No, great. Thank you very much, Adam, as always. I just wanted to remind people, as I was saying, of these other methods, which, as I said, are sort of a little bit closer in philosophy to this pre-coding. So, these other approaches, in particular, I'm just going to mention InstaHide, also do a pre-mapping, okay, and then the learning on this pre-processed data. However, they were found to be fragile and they were found to be fragile to the following attack, which is a little bit like a GAN attack in effect. So remember that I emphasized, and this is the reason why, that the original data is that we know of what type it is, right? So we know that, say, it's a whole bunch of X-rays of chests, and therefore there will be public data repositories which are similar in many ways to Alice's data. Okay, and so one of the ways in which, for instance, the InstaHide attack was broken by a group at Google, Carlini and others. InstaHide was a project that came out of Sanjit Arora's group at Princeton, is that they took a publicly available data of a similar ilk to data that, in their case, it was sort of combining their own data with other publicly available data. But in effect, they took publicly available data of a type that was similar to data that was being used to hide the other information. And they basically compared, processed and compared the distributions, and in fact, tried to learn the mapping. Okay. And by learning the mapping, then, of course, you can try to then reverse engineer the mapping. And that is why we ended up not going with a linear model for the pre-processing. Here's a normalized mean squared error. You can see that, because we did something nonlinear, we got quite a bit of benefit relative to doing a linear approach. Okay, so this adversarial attack, which we had seen to be successful against other previous systems such as InstaHide, we were able to not fall foul of. Okay, now we have another possibility of attack, which is one where we're just looking at aiming to protect a sensitive attribute. So for instance, a gender predictor, just as one example of the sensitive attribute. Again, remember that the label we're not trying to protect. It's almost by definition we cannot, because the data has to be able to provide the information there that allows the label to be learned. Okay, and what you can see is, again, that the nonlinearity neurocrypt does provide quite a bit of benefit over something like just a linear system. Okay, now Adam and et al. Put together this fantastic challenge on GitHub. And challenge 1, which is a simplified setting where the attacker has access to the plain text version of the encoded data. So, this is, if you will, a highly highly enabled attacker, highly powerful attacker, because the attacker already has the plain text version. So, you can wonder, if the attacker has the plain text version, then why is the attacker even trying to, to gain access to the plain text? They already have it. But, let's just, this is an attacker with, every trick in their bag. This was recently solved by a group at Google. Well, I should say it's not quite solved. The first version of challenge 1 was broken, and there are other versions. And the second challenge is an attack scenario which is closer to what one would consider a likely setting. The attacker there only has access to distributionally matched plain text data. That's to say, that's closer to this type of attack that I mentioned before, where the attacker doesn't have the original data, because heck, if the attacker has the original data, why is the attacker trying to get the original data? They already have it, right? It seems a bit odd, but the attacker has access to data which is distributionally close to the data that they're trying to gain access to, right? So challenge 2 has remained open. Now let's go back to this idea of the pre-image. We talked about choosing a key. Okay. One of the most simple versions of a key is, of course, a password. Okay, and when you consider, say, the the security of a password, you actually have a very interesting notion, that of guesswork, which I'll talk about in a little bit, that becomes actually the essential notion in looking at security of passwords. So based on this, we're actually introducing here, if you will, another challenge, which is probably a challenge which is, let's say, more realistic for still a very capable Eve. And this would be an attacker has access to the plain text version of encoded data and is trying to identify at least one correct pair of plain text ciphertext. So what does that mean? For instance, when you think of, people deploying botnets and, trying to guess a password, really they declare victory if they manage to maybe break one person's password. Okay, so if they manage to figure out one person's password, then in effect you think, okay, they have breached the system. All right. So here where we're going to worry about not necessarily having Eve figure out the mapping and being able to sort of recover the original data. What we're really going to worry is about Eve figuring out in at least one case a mapping from the plain text, that's to say the image of the person, to the ciphertext. Okay, and in particular, this means that we are worried about privacy if even just one pair is revealed, not necessarily the entire mapping, but if somebody is able to figure out, that is Muriel's X-ray, then that's a problem, right? Whether it's Muriel's X-ray or Adam's X-ray, anybody's X-ray, then that's a problem. So this is actually an approach which is closer, as I said, to sort of password protection. That's an area in which Ken and I have actually, and our groups have done a lot of work. And the general framework for considering password protection is that of guesswork, which is basically the number of guesses that it takes for an attacker to be able to break a password, or in this case, to re-identify a single image without having access, of course, to the private key, right? Because it would be like, if somebody knew already your password, then the number of guesses they have to do is one, right? They already knew it. So basically what's going to happen is that Eve is going to make a guess in the form of a mapping between X and Z, okay? And the guess is correct if indeed Z was the image with the transformation of the original X, of the original image that was transmitted, okay? Just a couple of definitions. So a guess is representing the matching between, again, this X and the Z. And of course, how are you going to guess? Well, you're going to guess from most likely to least likely, okay? And the ranks, there's a little bit of a shift here, is the index of the first correct guess in your strategy, okay? So all of guessing is really about describing these distributions, okay? And what happens is that what's interesting in much of the guesswork is that it can be expressed very differently from traditional or maybe the more familiar forms of entropy that you may all remember, say from information theory. And in particular, rather than looking at Shannon entropy, this is described in terms generally of moments of Rényi. The moments of guesswork are described in terms of Rényi entropies, which is a generalization of Shannon entropy. And we can, happy to talk more about it. We didn't want to put too much in here. Anyway, so basically, for any given strategy, Eve's posterior distribution on the rank, basically of this guessing, is going to be according to the observations that Eve has, and to what extent these observations aid in the guessing, okay? And you can imagine a variety of different metrics. One of them might be the expectation. So, basically, this is the index of the first correct guess. So when's the first correct guess on average going to happen? That's this first metric here. You could also look at basically a somewhat different approach, which is let's maximize over all of these different over these given the observations, what's the probability that Eve only has to guess fewer than k times. Okay, so that's to say, if say Eve has a guessing, a complexity budget, how many times does it have to happen? I just want to make a small remark here, because again, this is a very powerful Eve. This assumes that if Eve guesses correctly, she's able to find out that that guess is correct. Okay, so it assumes that Eve has access to an oracle. An oracle that says, oh yes, Eve, you're right. That is indeed the encoded version of Muriel's X-ray. Okay, so that's also giving Eve a whole lot of power. In practice, if you were to look at something like this, what would happen is that Eve would have to make the guess, say, well, I think that that was Muriel's X-ray, somehow or other go and find Muriel's X-ray and be able to somehow confirm, which would be very, very difficult because Eve still doesn't have access to this mapping T of A. Okay, so in effect, she would need to have access to an oracle, which would be almost as hard as finding T of A itself. So again, this is still an approach that is providing Eve a huge amount of power in a way which we just don't see how Eve could have it. Okay. So we rank the guesses. I'm not going to go much into it, but the idea is again that you're trying to map the z's to the x's, and each z could have all these x's as pre-image, and you guessed correctly if indeed you managed to get the right match. Suppose that this was the right match. That means if any of these you guess the right point. Okay, think of this as sort of playing Battleship. If you guess one of them, though, here you've won. And of course, this could be generalized to guessing 2 or whatever you wanted to do. And with that, what do we do? So you have a deep neural network, which is going to be estimated to train. Okay, basically, how would you figure out the guessing? Basically, here what you're doing is you're training to you would be training the guesser. Okay, so the interesting thing is what you would be doing is in effect training to knowing which input goes with which output, okay, which is basically like training to get the identity function. Okay, and this is basically the method for being able to create this guessing grid and being able to estimate what is this optimum way of guessing. The guessing itself is very, very hard to figure out. Okay, so you're basically doing a training in order to provide the guessing order to construct the guess grid. Okay, and the interesting thing here is that if you look at something like InstaHide or Dauntless, the training is very, very effective for this guessing. The average strategy rank, the number of guesses that it would take, is 1. Okay, so from the point of view of security, looked at it in this sort of more password-inspired version, they're a disaster. Okay, if you look instead at Cypher, you're looking here at over 7,000 guesses. Okay, so over 7,000 guesses, that is actually similar to having a really non-trivial size of a password. Okay, if you look at password protection, that's actually a non-trivial size of password. So basically what you've done here is you have secured it in a way which can be mapped back to a nice size password. And also one of the things that's interesting is that if you look again, at sort of how good the utility has remained, how good the learnability has stayed. The baseline here is basically not not encrypted, not encoded in any way. Of course, it's a little bit of a hit, but it's a much smaller hit than, for instance, insta-hide. Okay, so you're getting really a very, very nice security, again, with this notion of guessing, which is so very central to much of the to much of what I would call sort of more statistical view of security, particularly around passwords. So with that, I'm getting close to the end of the hour, and I want to leave time for a couple more questions. But this is what we've been working on. It has been just a ton of fun, highly interdisciplinary. Again, want to, as always, thanks Regina for pulling together such an amazing team. And I'm happy to take questions. And of course, several of the co-authors are in the audience, and we can collectively take questions. And I see Aria. Aria is a co-author. She's happy to. Oh, there's two Arias. Okay. There's three Arias. No, two. Oh my goodness. All right.
Question. Yes. Maybe you can say who you are.
Muriel, hi, this is Pete Solovich. I want to go back to David's question. I mean, it seems to me that if the various analyses at different institutions chose, let's say, permutation functions, random permutation functions, then it seems to me obvious that the machine learning method would have to learn much more than if you just gave it the original images, because somehow it has to be able to invert those random transformations.
So let me start out by saying that the permutations would be a subcase of linear, right? So as I've mentioned, the linear is not going to be a good choice from a security perspective.
Okay, so that's too simple a case, but let's suppose, if I do some worse transformation, I think the point of the argument is, wouldn't the machine learning model have to learn a lot more than it has to if it's given the original data? I think Adam is anxious.
I see.
Yeah, so I want to clarify that this is not about using any function to do the transformation. There's a very careful design on how to pick a function such that you can actually efficiently learn while taking privacy. If you use the identity function with no privacy, there's plenty of functions that ensure that you put up privacy, that multiplying by zero, they give you no utility. And you can choose specific function families that have consequences of the downstream model that make learning even harder. For example, if you took something like NLP that scrambles function structure, you have the downside that now you have lost sets of bias. So you can't use things, you can't use interfaces effectively. But conceptually, all which is still preserved through that function. So there's an active design problem that's not shown here. Is the how we went about that design problem. Specifically, Eurocrypt takes one particular view, uses hash up into differences, something like neighborhood correlations. And that's specifically because we were kind of reducing the scale up. We're kind of reducing scale up to almost like a silent and surprising. Software takes a stronger approach and a stronger technology, any one desk along the way. And what's written there in the slide before is that this is about preconditioning the data space such that the most but it's not like a 180 cognitive avoiding function.
Cipher and Eurocrypt are completely different papers, right?
Yes. We can send you the next one.
Just separate, they're different things.
Different things are kind of like stronger. One has a stronger technology.
What we call
Speak into the that you're holding, not the box.
yeah. Oh, here, that makes more sense. What we call as algorithms in our coding is a family that each one of the encoders in the family will preserve the utility. So they are designed to preserve this utility. What Alice does is she randomly selects one of the encoders in the family. So no matter which one of them, they will all preserve the utility. The privacy comes from the fact that even if we assume Eve knows the family, knows all members, but she doesn't know which one was selected. So the privacy comes from like the ambiguity between that set.
In a way, there's like a secret character to see, which is the computer scientist designing this encoded family to achieve these properties.
Okay, yeah, now let's go to Felix. Felix, you first need to figure out how to use this device. It's like intelligence test.
I guess so. As like a follow-up question to that, how difficult is it to design these encoder families? Like, if you have a new task that's maybe not images that you haven't worked on before, how difficult is it to like come up with a good family? Like, is there a general framework where you're like coming up with a good family?
Sorry, can you repeat the question? I had a little bit of trouble hearing it.
Oh, sorry. I was just asking how hard it is to design this family of encoders, sort of to ensure that you can still learn the property that you're interested in and have this privacy.
So
That's a good question. Because in a way, we know it's sort of a little funny. I didn't go much into it. There's an existence proof that they exist. Okay. The question is, when you found them, it's hard for you to know whether you actually found them. If that makes sense.
What is the existence proof?
The existence proof is that there is a family of encoders which would provide the perfect privacy. Now, the question later is, when you picked a particular family, you don't actually know whether they provided whether those did actually provide perfect privacy or not. So there's two aspects to your question. One is around the building of the perfect privacy part, right? And the other one is around the building of encoders that will then allow learning, which is related to David and Pete's question. So in a way, once you found a family, you can verify empirically whether they permit still good learnability, right? So you can find out right away whether they permit good learnability or not. The thing that you're not quite sure, of course, is, did you actually pick from a correct family? You know that there is an existence proof that there is such a family, okay? And by the way, as information theorists, we're very comfortable with the fact that there is an existence proof. That doesn't mean necessarily you know how to find one. There is an existence proof of this perfect privacy set of mappings, but figuring out whether you actually are in that perfectly privacy set of is not clear, which is why basically you need to have the challenge is you need to be able to figure out whether somebody can break it or not. And the longer it goes without being broken, in effect, you're inferring that it's more likely that you picked from the right family.
Adam, do you want to elaborate?
yeah, I want to add something. In the follow-up work in Cypher, we have a efficient estimatable computational scheme to assess the privacy, which then also acts as an optimization criteria for designing the family. So per modality, like on imaging, we have some results on X-rays now. We expect that if we retrain the same scheme to develop this level of obfuscation, we can easily do other. The same kind of design pattern principles and also built other types of modalities that's still not yet explored. But having an efficient way to test this is part of the reason why I guess mechanics is so important. Efficient estimation of this looks so important. And that doubly then acts as a way to design. Now, but the thing is, with any kind of estimation scheme, there's always a possibility that maybe there exists a new way to train things that is not kind of captured by this. Like it kind of considers a specifically kind of conflict with bounded adversary with this kind of estimation in terms of the kind of model. And so that's also a kind of particular challenge and similarly speak any other kind of script.
If I just follow up, so when you're also
like when you're assessing the learnability, so like what's your assumption, like in a practical case, because obviously you couldn't like compare the performance of your model if you had trained on the aggregated data set, like plain text versus your encoded scheme. So would it just be like you assess on, you have access to one of these data sets maybe, and so you assess like learnability on that or something, and then does that estimate learnability for the whole set? Because like maybe one hospital has something that, you know, the distribution is very different or something from a different part of the world. And so maybe like your encoding scheme is, you know, obfuscating something in that sort of distribution, but not in the one that tests them.
So I think it's important to understand the type of obfuscation that's being provided, because you do not necessitate actually destroying data to achieve that. So imagine something, imagine the data is very simple, it looks like a Gaussian distribution. Then even like random rotations that you put in privacy without putting utility at all, because you consider not to put targets for rotating. Now the trouble is that regular true data distribution don't have this problem. So part of the work in Cypher is kind of creating obfuscators, is conditioning the data such that it gives you distortion. So you do not need to lose utility in principle to achieve this. So they kind of joint object criterion is a mixture of both full reconstruction of the machine, trying to marginalize all possible tasks, and pooling and ensemble adversaries trying to do this kind of very hard guessing game, in which any one guess correctly with a completely matched data sets with another. In general, this is it's easy to like imagine like it's very easy to understand why this is feasible in general. And then you can feasible for arbitrary data retrieves and arbitrary data distributions, and that's where the very is involved.
So since we are already running out of time and I don't want to hold everybody, of course you can continue the discussion. Just
Yeah.
please thank very much Muriel for great talk.
Thank you guys. Thank you all for and we'll I'm sorry, I'm being called to the next meeting. So
Yeah, no worry. Bye. Bye. Bye.
thanks. Bye-bye.